graph, we have to find out whether the Hamiltonian cycle is present or not. In case the Hamiltonian cycle is present, then we have to rewrite all the Hamiltonian cycles. Okay, so here our the main thing is for a given undirected graph. Okay, we have to find out the Hamiltonian cycle. Okay, we want to find out what are the Hamiltonian cycles are present in my given graph, and then generally this kind of Hamiltonian part, okay, can it is the undirected graph. Okay, the main purpose is, okay, again it has to start from the starting vertex, and then we have to visit all the rest of the vertex, and we have to go back to the, after visiting all the vertex, need to go back to the starting vertex. Okay, so now the main purpose of Hamiltonian cycle is we have to visit all the vertices at least once, and we want to return back to the starting vertex. Okay, you can think whether the traveling salesman problem and Hamiltonian cycle both look like same. So the main difference between these two is traveling salesman problem is mainly for the optimization. Okay, that is we are finding out the minimum cost. Okay, among all the possibilities, which one is having the minimum cost. Okay, that we are going to find out the minimum cost to visit all the vertices in your graph, and then it will go to the starting vertex. But in case of Hamiltonian cycle problem, we are not going to find out the minimum cost or the minimum distance. Simply we are going to find out what are the possibilities of the Hamiltonian cycles, what are the maximum possibilities of the Hamiltonian cycle in your given graph. So that is what we are going to find out here in this Hamiltonian cycle problem. Okay. So generally, if the linear graph in all the vertices are connected, means we can able to find out the Hamiltonian cycle. So let's take this particular example, this particular graph. Here I am having 6 vertices, 1, 2, 6. Okay. So now these are all the possibilities. Okay, these are all the possibilities of Hamiltonian cycle. That is, I am going to visit all the vertices only once. Okay, and we have to start back. We have to visit again to the starting vertex. So now listen, see 1, 2, 3, 4. Okay, and then 5, 6, 1, 2. Okay, now 1, okay, 1. Okay, so 1, 2, 3, 4, 5, 6, 1. So this is one possibility. Okay, and this and next this is one possibility, and next possibility is 2, 3, 4, 5, 6, 1, 2. Okay, see, listen. Okay, and the next possibility is 1, 2, 6, and then 5. Okay, so 5 to 4, 4 to 3, and 3 to 1. So this is one possibility, and this is third possibility, fourth possibility. So listen here, we will be having 4 possibilities, 4 Hamiltonian cycle, and but here that will be having duplicate. So that thing should be avoided in the Hamiltonian cycle. So what is the duplicate? See, listen. Simply this is one possibility. 2, 3, 4, 5, 6, 1, 2. And see, again this is also 1, 2, 3, 4, 5, 6, 1. So here both in this particular diagram, see 1, 2, 3, 4, 5, 6, and here this is the not a connected graph. This is the unconnected graph. So why it is unconnected graph? See, this is what will be this 4 we will be taking as a pendant vertex. So pendant vertex is, see, there is no connectivity between 5 to 2 or 5 to 1 and even 6 to 3 and 6 to 1, right? So in this kind of graphs we cannot able to create the Hamiltonian cycle. Okay. So now I will take one example. From that example given from the graph, I will tell you how to take the Hamiltonian cycle. Okay. Okay, so I take one example. A, B, okay, fine. And here my starting vertex is A. Starting vertex is A. Fine. So now I'm going to construct the state space tree. By using state space tree only, I'm going to perform the backtracking. Using the backtracking only, I'm going to find out the Hamiltonian cycle of my given graph. Okay. So state space state so what is the starting vertex? I have taken it. Okay, the starting vertex is A. Okay, so from A, okay, so from where, okay, so you can go wherever you can able to go. So from vertex A, okay, then what are the possibilities? You can able to go, you can go B, C, and D. Okay, so before getting into this, I will tell you what is the meaning of state space tree. So state space tree means the starting vertex will be your root node. The starting vertex will be your root node. From the root node, okay, you are going to create the next level of trees, next level of nodes. Okay, so you have to go next level component. Okay, whenever the next level component further you don't have a next level component. Okay, that is the dead end. You cannot able to create, or you cannot able to go further trees, further nodes. Okay, so that is what the dead end. Okay, so at that time you are again after finding the dead end, again you are going back to the previous state, and then you are finding whether all the next level components are there or not. In case the next level component is not there for a particular node, again you are backtracking to the previous state. So like that you are you are performing the backtracking in your tree. Okay, so that is what we are going to do here also. Okay, so first starting node is A. From the node A, you can go B, C, and D. Okay, so now actually it follows the depth first stage. So this depth first. Okay, it will go depth wise first. Okay, so now from A, next it will go B. So from B, okay, so from B, wherever you can able to go, you can go A, C, and F. Okay, so already A is already visited. Okay, you should already visited, so that you should not take that A. So simply I am taking C and A. If I am taking C, the next answer letters are D and E. Okay. If you are taking D, okay. So if you are taking D, so who are the neighbors? Tell me. A, C, E, right? So already A and C is visited, right? So who is the next? E. Am I right? So from E, what are the neighbors for E, ma'am? D, C, B, F. D, C, B, F. So already D is there, C is there, B is there. E is not there, ma'am. F is not there. I'm taking F. Okay, ma'am. So from F, what are neighbors of F, ma'am? What are neighbors of F? B and E. So check whether B is there, B is there, B is there, and E is also there. Okay. Now the thing is, next after visiting all the nodes, I want to go back to the starting vertex, that is A, right? So I want to check whether there is any connectivity from F to A. Do you have any connectivity from F to A? No. This is your dead end. This is what your dead end. There is no further next level component. Okay. So that's why I'm going to perform the backtracking. So backtracking means you are going to E. Okay, so who is the previous state? D. So who are the neighbors? D, C, B, F. So D, C, B, F is already there. Okay. So D, C, okay. B is there and F is also there. F is also visited. All are visited. Okay. So you cannot be able to do. So next you are moving to the next thing. That is what? Next you are going to D. Okay, so from D, okay, what are the neighbors? A, C and E. So E is already visited, A and C is also visited. Okay, again there is no more nodes. Okay, so again we are moving to the next node, that is C. Okay, who are the neighbors of the C? Who are the neighbors? A, B, D, E. So A is there, B is there, E is there. Who is not there now? Who is not there? Okay, so A, okay, we are taking C. Okay, so in this C, who are the neighbors? A, B, D, E. Okay, so okay, A, B is there. So from this C, you are coming to E. So from this E, who are the neighbors? D, C, B, F. So from this E, who are the neighbors? D, C, B, F. B is there, okay, and then C is there. Who is not there? Okay, so from this E, the neighbors are D, C, B, F. So B is there, C is there. Who are not there? F and D is not there. So I am taking B and F. Okay, clear? Okay. So I am repeating again. So we are going to get edited. Okay. Again we are doing the backtracking. We are going to E. So when we are going to E, all the nodes are visited in that particular path. So again we are going backtracking and again we are checking with B. So all your neighbor nodes has already visited and again we are going to C. Okay, in this C, okay, there will be having another branch, that is another thing that is called E. Okay, from the E, okay, wherever you are able to go, D, C, B, F. Okay, you just check this path alone, this path alone. Okay, so here B and C is already visited. Okay, B and C is already visited. Who are not visited? D and F. So that is why I have D and F. So that are the unnecessary rule. Okay. So now we will be having now this step D. So who are the neighbors for D? Who are the neighbors A, C, E? Okay. See, A is there, C is there, E is there. So now, okay, it is okay. Do you have any step here? That is no, all the nodes are not coming, right? F is missing here. Okay, this is the dead end. Okay, so come to the F. So who are the neighbors B and E? So B is there and E is also already visited. Okay, there is no connection between F to A. So that it is also dead end. Am I clear? So come to the from so after that come go to back to B. Okay. So from B. Okay. So from B you can have okay we have the F. Okay. What are the neighbors from F? One second. Okay, so who are the neighbors of B, A, C and F? So from this B already I am having F. Okay, who is missing? C is missing. Okay, so I am taking so C is also. Stop. So here, after performing the backtracking, we are going to the B, right? So the core of the axis of the B. So the B from B can go to A, C, E, F. Okay. So the C spot is over. So who are there? E and F is there. Okay. So now come to the F. So now from B are going to F. So from F, wherever we can able to go, you can go B and E. Okay, B is already there. Okay, that's why I'm going to take only E. Okay, so from this E, wherever we can able to go, we can go B, C, B, F. Right? From B you can go D, C, B, F. Okay, so already B and F is there. Who is missing? D and C is missing. So that's why I'm taking D and C. Just take D. So from D where can you able to go? You can go A, C, E. Okay, so already A is there, E is there. Who is missing? C is missing. So I'm taking C. So from this C where you can able to go? A, B, B, E. Okay. So already I am having A, B, B, E. Okay. So that is no more neighbors. So next thing I am going to check this as I have to go to the starting vertex. Okay. So what is the starting vertex? A. So I am going to check whether I can able to go from C to A. Yes, it is possible. I can able to go from C to A. So now please check this is the solution one. Okay, this is the first Hamiltonian cycle. Right? A, B, C, D, E, F, A. So I have visited all the vertices one by one and I have to start. I am going to the starting vertex. Okay, so this is your part 1. So this is your Hamiltonian cycle part 1. Cycle 1. Okay, and now, okay, so after receiving my solution, I am going back to the E vertex. Okay, so from the E, where I can able to go, I can able to go C. Right? So from C, where I can able to go A, B, D, E. Right? So already I am having A, B, E. Who with the previous okay. So the rest of the rest the vertices are like C and B. Okay, from C we can go to B, from B we can go to E, from E we can go to D. Okay, so from B we cannot able to go anywhere. This is the end. Okay, now just go back to B. So from the B, you can split the result. B also already split. Okay, I'm splitting this A. From there, we cannot get it to go A. This is the way. Okay, just go back to B. Now back to B. So from B, okay, the answer is yes. Okay, from the F, the answer is E. From the B, the answer is D. From the D, the answer is E. Not answer is so here we have split all the vertices C, A, B, C, D, E, F. Okay. So finally, we have shaded this. We can connect whether D to A or D to A, then it will be connected. So this is the solution 4. Okay, so our solution B. Okay, this is the solution D. Okay, like that. Go back to C and then check the next possibility is D. So from the D, okay, the answer is E. From the E, you can go to the answer is one is B, another one is F. From B, you can go to F. But okay, that's no that's right. So now go back to C. So here another answer over the step. And here you can go B. From B, you can go to B. So then from this C A to B, C to C. B, E, F, F, G, and B. All the tests are there. Okay. So I have to think whether I can go from D to A. Still that is possible. So that is why it's solution 4. Okay. So this is one lady. This is one part. This is one part. Okay. So now after seeing this, just go and check whether any good Hamiltonian cycle is possible or not. Okay. Go to see that the possibility is E. So from the E, all the answer that exists F and B. From the B, the answer that exists F is also not possible. So go back to E. Go with D. So here, D is possible, but here only A, C, D is there, but B and F is not there. So this is not the right cycle. So now go back to B and check who's the next one, F. Okay, so from the F where you can able to go, you can able to go B. So you have visited all the B adjacent vertices. Okay, from the there are some vertices are missing here. So also you cannot able to take it. Okay, now go back to A and come to the next thing that is D. So from D you can go to C and D. Okay, so like that you have to visit all the vertices. Okay, and you want to find out the constant Hamiltonian cycle. Okay, so from the C branch, we can able to find out two solutions. That is A to B, B to C, C to E, F, F to B, B to A. So this is one cycle, and the next cycle is A to B, B to E, and then E to F, F to B, B to C, C to K. This is the understanding. So, totally in the given graph, we are able to find 6 possible Hamiltonian cycles. So, that is what solution 1 to solution 6. Okay, so this is how we have to find out the Hamiltonian cycles. So again, I'm telling you this Hamiltonian cycle problem. We have to start from the starting vertex. From the starting vertex, okay, we want to present all the rest of the vertexes here in the, and again you have to go back to your starting vertex. Okay, so here in this, we are not going to find out the minimum cost or minimum distance. Simply, we are going to find out how many possible Hamiltonian cycles we can able to make it by using the backtracking method. Using the backtracking, so first I'm constructing the state space tree by using the backtracking method. I'm going to find out the Hamiltonian cycle. So as I already told you, for a given graph, there will be having many possibilities of Hamiltonian cycle. Okay, so this is how you want to find out the Hamiltonian cycle for a given graph. Okay, thank you.